actually begin the discussion on multi-axial formulation. And in today's class, we'll be covering the very basic parts of it. So you can consider that them to be the preliminary towards the multi-axial formulation. So let's start with that, and that requires a certain amount of recollection. So recollect the following from what we have learned in the finite element course. So so we are doing basic linear algebra. So not just finite element course. This can be thought of recollection from the basic linear algebra. For example, recall that these are there are three invariants for uh, general matrix T in Lin. So Lin is a set of all 3 by 3 matrices. Uh, okay, so the I1 is actually the trace of the matrix T, and I3 is uh, is the determinant of T, and I2. To understand what is I2, you see, for any general matrix, okay, let's say n by n, so there would be T11, T22 up to Tnn. Now T can be both symmetric and skew symmetric. It doesn't matter. Okay, so this thing is T1 to T21, then T13, T31, T32, T33, T23, T1n, T2n, Tn1, Tn2, Tn3, up to Tnn, and this goes to T3n and eventually to Tnn. Now, now it's the sum of the principal principal uh, determinants of rank m, where fall for, so m is anything between 1 to n, 1 and n, any integer between 1 and n. So that becomes an invariant. Now I would explain what I mean by that. For example, uh, if m is 1, then the first in principal determinant should be sum of the diagonal terms. So the first one is T11, okay, so principal determinant, then some T22, then T33 up to Tnn. So I1 is a trace. And similarly, the im actually uh, is when sorry in not m in is where you take the entire matrix and get the determinant of that. But since it is supposed to be a sum, uh, I mean, there is no way to sum that because there is just the whole matrix. So that is actually the determinant of t. Ideally, it should be done uh, n times. But uh, let's say I want to talk about I2, then the sum would be determinant of this portion. Okay, so T11, T12, T21, T22. Okay, then add to that, add to the next principal determinant of size 2. So next goes this quantity T22, T23, T32, T33, and so on. But when you reach, let's say, uh, the nth sum, there you actually go back to uh, T1 as well. So the last determinant in this series should be something like TNN, T11, then over here Tn1 and T1n. So it simply cycles back. So you get the idea, right? So you are supposed to get the determinant of all of these quantities. Okay. Um, okay. So you need to keep on doing this, and all of these become invariants. And the number of invariants actually depend on the size of the square matrix. So if it is a square, okay. So this one is a square matrix that needs to be
Sir,
mentioned.
sir,
Huh. Yes.
sir, last কি করে হলো একটু বলুন last determinant T n n n T n on.
Yes, the thing is, once you reach, okay, so if you keep on doing this, see, you are taking two elements to construct a matrix. Okay, so by the time you had two matrices, you are taking two rows, right? So you have consumed three rows, but you are actually supposed to repeat the process n times. Actually, this thing is also n times. Okay, but since n is just a number which is a constant for a given size, so n is skipped in this case. Simply the determinant is taken. Now if you keep on repeating this, by the time you reach the last row, you would actually be having n minus 1 sums. Okay, and that is not sufficient. You are supposed to do take up to n sums. So when you take the next sum, okay, you just imagine that this t continues to uh, infinite number of rows. But when you reach tnn, okay, after that comes your t11, and you need to imagine this thing is n1 n2, as if the first row or the first index is also the n plus 1th index. You'll have to imagine it like that. So you'll have to circle back. So when you have I3, let's say, so you'll have to circle back with the this t22. Okay, so after that it would be tn2. So sorry, this one is T1n. It is supposed to be T1n. Then T2n. Then if you have to do I3, okay, for T, then it would be 1n, 1 1, then 1 2, then 2 1, then 2 2. And actually you'll have to imagine that the number of rows in t are like infinite, not really, but just to calculate the invariants. Okay, and you can simply substitute for n plus. You see, when you come to calculate the uh, nth of that matrix, Okay, nth of that determinant. Okay, so you have tnn. Starting point would be tnn. Okay, because until now you only had, let's say for I2, n minus 1 number of determinants. So when you want to get tnn, I mean the nth determinant, so the first term is tnn. That is for sure. But then if you were to proceed further, it should be tn n plus 1. And then this term should be tn plus 1 n. And this term should be tn plus 1 tn plus 1. But the matrix T has only n rows and n columns. So actually, instead of n plus 1, you should be using the first index. Okay. You need to understand that this is also not so you'll have to do that rearrangement for every such every such mm, determinant. Okay, every such ith determinant or mth determinant. Okay, so that way, but let's not focus go up to n by n matrix, but that is the general rule. Okay, and for a matrix of size n, that is how many determinants do you get. But we are working with 3D vectors and matrices, so you'd be happy with three invariants. Okay, so let's say if T has only this many rows and columns, 3 by 3. Okay, can you give me the expressions for T1, I1, I2, and I3? Can you calculate those expressions? Can you calculate I1?
Sir, I on T on plus T22 plus T33.
Okay, so I1 is the simplest. So T11 plus T22 plus T33. Okay, and I2 is also very simple. So you need to just give me the determinant. What can you tell me the expression?
Sir, করছি আমি।
Sir, I11 into I22 plus I22 into I33 plus I33 into I11.
T.
Yes, those are T. And
Hmm.
minus T12 square minus T23 square minus
No,
T31
no, no,
square.
no, 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 no. You are wrong here. T is a general matrix. T is not symmetric. The point being T1 and T21 are not same.
Okay, sir.
Sir, T on into T22 plus T22 into T33 plus T33 into T on minus bracket T on 2 into T two on.
Oh, sorry. Yeah, I made a mistake. I made a mistake. Yeah, it's not the expression, right? Uh, I, okay. So this is a I3 that we are talking about. Are you telling me the expression for I3?
I3, sir, I3 বের করিনি এখন I2 বের করেছি।
Okay. So you have the expression for I2, right? And how much is I2 again?
T on into T22 plus
Mm-hmm.
T22 into T33
Mm-hmm.
plus T33 into T on
Mm-hmm.
মাইনাস ব্র্যাকেটে মাইনাস করেছি স্যার এটুকু লিখেছেন না এক মিনিট T33 into T on minus T3 on into T on 3
This one, right?
হ্যাঁ স্যার
Now, now you can also get the expression for the determinant, which is very straightforward. Okay, so you can do that later. But the point I'm trying to make here is is uh, that in the previous course, in the finite element course, we also talked about how they are invariants. Okay, we showed that those are invariants. Okay, so to do that, I mean, just consider this to be a recollection of that. So to show that these are actually invariants, okay, let's try this. So let's try the I1 being the invariant. So for that, what we need to do is we need to start with the basic statement of linear algebra. I mean, basic identity of linear algebra, which is trace of AB is is trace of BA. This requires to be proved. Okay, so trace of AB is actually summation of all the terms mm, AB. Mm, so so if AB is a matrix C, so we need to take all the diagonal terms. Okay, so I goes from 1 to 3. So simply you take the diagonal terms and add them up, and that actually can also be thought of, because each term AB is can be obtained like this. Okay, so again, these summations are independent, and the order can be changed. uh, So, so this can be written as summation over j equals 1 to 3, summation over I equals 1 to 3, uh, bji and aij. And since j and I are basically dummy indices, so I can also write it to be I equals 1 to 3, summation j equals 1 to 3. So now this time I'm just switching I and j, because these are dummy indices, right? So they are taking different values across the summation. So it is bij aji, which basically, if you look at the previous expression, it basically represents trace of BA. And how does that help? Because let's say T prime is what you have obtained by looking at T from a different coordinate system. Or by rotating T. Okay, by rotating T by certain angle. So this is how you rotate a matrix. Or once you look at a matrix from a different coordinate system. Okay, so let's say this is your global Cartesian. Okay, and you are looking at it from a different coordinate system, x prime and y prime. So I'm not going into the details of the expression for q, but where q is an uh, orthogonal tensor with positive 1 determinant, which basically means that q is a, this set is uh, equivalent to the rotation tensor. It's a rotation tensor. So we showed that this rotation tensor can be showed with this thing, that q transpose q is an identity matrix, because that means the determinant, sorry, the transpose is an inverse. Okay, and that leads to the possibility that determinant of q is either plus or minus 1. But we would not take this. We'll only take the ones which have a positive determinant. Okay, in order for it to qualify to be a rotational tensor. So, or rotation tensor. So if I'm looking at a matrix T, okay, and that matrix could be the stress matrix as well. So if I'm looking at it from a different coordinate system, it would look to me like this. Okay, and of course the the expression for q needs to be determined, but q is an orthogonal tensor satisfying all of this. It's actually a rotation tensor, not just an orthogonal tensor. It's an odd plus tensor. Now, um, now if I take the trace of that, trace of t prime, okay, uh, so that would be trace of q t q transpose, uh, okay, but then I can segregate q like a, and then t times q transpose like b. Okay, so that way I can say that this is also trace of uh, t times q transpose q, and as you know that q transpose q is an identity matrix. Okay, so this I'm using this identity over here to show that this is simply trace of t, which basically means that the trace doesn't change with change of coordinate system or with rotation. Okay, and that's what is actually the meaning of invariant. Okay, so that means I1 of q transpose t q, or q t q transpose, both actually are rotation tensors. Okay, is if that is equal to I1 of t, and if that is true for all q belonging to orth plus set, okay, that implies I1 is an invariant. Okay, and that needs to be satisfied by each of the invariants. So we will now proceed for the next invariant. So and it is easier to do I3. So I3 is simply determinant of t. Now let's try to take determinant of t transpose. You see, most of these have already been covered in the previous course, that's why I'm rushing through it. But if you want to a recollection, you can go through that video. It's available in the YouTube channel. So with um, linear algebra on finite element method. So there it would be cleared. So and I hope some of it you still recollect, so you'd be able to correlate. So if you take determinant of this, so that is determinant of qt q transpose. Okay, um, if I were to rotate a vector, I would simply multiply with single q, but to do that on a matrix, I'm supposed to do double multiplication. Okay, pre and post multiplication. So so there is another identity that I'm using here, which is determinant of AB is essentially det A times det B, and that's not I'm going to prove. Okay, I had just proved that this for trace. Okay, but I'm not going to prove this for determinant, but I'm going to use this, which basically means this is mm, acha. And this is also which basically means this is also determinant of BA, which means this is determinant of T. So again, segregate them into A and B. So this basically is T times TQ Q transpose Q. So again, this thing is an identity matrix. Uh, so basically, this one is det T. Okay. Now, so basically that means this is our I3. That implies I3 is an invariant. Okay, and now talk about let's talk about I2. Okay, I hope so far everything is clear, right? Is it clear?
Yes, sir.
Okay, so let's look into the expression for I2. Um, okay, uh, before going there, I need you to look at trace of t squared. Okay, so that would be summation over I, uh, summation over j. So t, actually, yeah, no, I'm not going to write it like this. So it is basically t squared I, right? And this is summation over I, summation over j is so t squared, it's simply t times t, right? So it is tij and then tji. Okay. So what I'm doing here is I'm simply taking the ijth term. So there are 9 such terms that I'm adding, okay, because I runs from 1 to 3 and j runs from 1 to 3. And each of those 9 terms are formed by taking first the ijth term and multiplying with that the corresponding ji term. Okay, for example, I can take, so it is starts like this. Let's take I equals 1 and j equals 1. So it is t11 squared. Then the next term, if I take I equals 1 and j equals 2, that would be t12 times t21. Okay. Now, can you find out the expression for trace of t squared? You understand what I'm doing here? Uh, Actually, trace of t squared is trace of t times t, which basically means I'm supposed to multiply. So I'm supposed to do this. So this is basically just like trace of AB. So this is t times tii, and then I'm bringing in another dummy index j to represent how the summation works. So each ith term of t squared is basically summation over j, tij, tji. Then you need to continue with this double summation. Okay, so there would be 9 such terms. So for example, next term would be t13, t31, and then you can go for the first index to be 2. Okay, so continue with this and get the final expression. And try to get the trace of the t squared matrix. So could you get the expression?
স্যার করছি।
Okay. Acha, mm, uh, so one of you can do this. The other person, I need to do this. Uh, at least one of you try to get the trace of t squared, which is basically t11, t22 plus t33 squared.
Sir, mm, I trace of t square করেছি।
This one, right?
Yes sir, yes sir.
Okay,
Sir, t21 into t12 plus t22 square plus
okay.
t.
No, hold on a second. When you said T21 times T12,
Yes sir.
is it not this quantity?
Oh, okay sir.
Okay. Then T22 squared, and
uh,
then there would be
t23
T
into. Yes sir.
T32.
Yes sir.
Okay. But the next term is T31 T13, which is basically this.
Yes sir. Yes sir.
And the next term is T32
t2
T23,
into
which is
2 3.
basically this.
Yes sir. And then plus
Sorry.
t33 square.
Okay. And now if I do this quantity, trace of T squared, can you tell me what's the expression that you are getting? Now I need you to calculate. So first, this is very simple, right? A plus b plus c whole squared, right? Everyone knows the formula: a squared plus b squared plus c squared minus plus twice ab, twice ac, and twice bc. Okay, so I need you to get this expression: trace of t whole squared minus trace of t squared. Try to get this expression. Are you getting this expression?
করছি স্যার এটা। So T22 square plus T11 2 into T11 T22 plus 2 into T11 T3 plus 2 into T22
What is the first term that you
T33
said? What is the first term in this?
T22
No,
T22 square.
no. There would be no T11
স্কোয়ার
squared.
গুলো
No.
থাকবে না তো?
স্যার হ্যাঁ স্কোয়ারগুলো কেটে যাচ্ছে সব।
Achha, you might have got some expression, and I am trying to be anticlimactic here. Just check this if this is correct. Is it correct?
স্যার আগে বলবো?
No, just check if this is correct.
Yes sir, correct.
Okay. Which basically means, is it turning out to be true for everyone?
Yes, sir.
Okay. So the point is that this is the expression for I2. This whole thing divided by 2. And now, so this is I2 of t. Now try to get I2 of t prime. So that would be trace of t prime squared. Now trace of t prime is trace of t, right? So this is trace of t squared. Then comes trace of t squared. So trace of t times t, right? So here I should be writing t prime squared or t prime times t prime, which is essentially q t q transpose q t q transpose. Now please note what happens to this part. This is an identity matrix, and then that makes this quantity to be trace of q t squared times q transpose. Now trace of t squared is an invariant of t squared, which basically means if I rotate t squared with q and q transpose, it's going to remain the same. So this is essentially trace of t squared, which basically shows that this is I2 of t, our second invariant. Okay.
স্যার এটা আরেকবার বলবেন?
Which part? You see,
স্যার ওই ট্রেস টি স্কোয়ার যেটা হচ্ছে।
okay, so yes, just like trace of t is an invariant of t, and trace of t prime or q t q transpose is same as trace of t because it's an invariant of t. You see, t is an arbitrary general matrix. T squared is also going to be another matrix, right? So if something is true for t, okay, if something can be shown true for t, that will also turn out to be true for t squared. Okay, because t is more general than t squared. T squared is a matrix which is square of another matrix. Okay, but t is a more general matrix, and whatever is true for a more general matrix is going to be true for any other matrix. Okay, so trace of t squared is also an invariant, which basically means once I rotate the whole matrix t squared, or look at t squared from a different reference frame, okay, so now that matrix looks like q t squared q transpose. Okay, so that is same as trace of t squared, because trace of t squared is an invariant of t squared. Is it clear now?
Okay, sir.
Okay. So now we will look for principal values and principal directions of, let's say, stress. Okay. Now stress, as we have learned, is a symmetric matrix. Okay. Um, because of angular momentum balance, and if there are no distributed moment, then it is a symmetric matrix. Okay. And we have learned from Cauchy's equation that this is the very purpose of the stress matrix. So you have your geometry and some supports here and there, and some traction here and there, some external load rather here and there. Okay. Now at any point within the material, within the continuum, okay, if I were to take an imaginary plane, okay, so exactly at point P, although I'm extending the plane to plus and minus infinity, but exactly at point P, the traction, which is basically force per unit area, okay. So let's draw the normal to this plane. Let's N be the normal. Okay, so the traction on that plane, let's say that would be T on that body anywhere within the material, that is given by this equation, and that is actually the purpose of Cauchy's stress, that gives you the traction at any location at on any plane. Okay. Now I may be interested in finding out how much of that is actually normal to the normal to the plane itself. That means how much of that is parallel to the normal axis, or maybe I'm interested in the normal and the shear component. This exercise is going to be very similar to how we used to draw mode support. Okay, but this time, instead of using figures and equilibrium equations, we are simply using Cauchy's equation and a little bit of linear algebra. So let's define Tn, the normal component of T, as n dot sigma times n. Okay, and okay, so So in initial notation, this can be written as first of all summation over I in I times sigma in I. So for that I need J in I sigma I J in J. Okay. You see, summation over J sigma I J in J is basically sigma times in I. So it's a dot product, right? So or you can think of a dot product like this. So what I'm doing is, so n is like this matrix, right? This vector, right? Nx, ny, nz, and t is something like this: tx, ty, tz. Okay. So what I'm doing is I'm doing n transpose. So this is 3 cross 1, and this is 1 cross 3, and I'm doing transpose of n, which would be now 1 cross 3 vector, which would look something like this: nx, ny, nz in a row. And when I do n transpose times t, it is basically multiplying a 1 by 3 matrix with 3, sorry, this one is 3 by 1, 3 by 1 matrix. And simply by using the rule of matrix multiplication, it turns out to be nx times tx, ny times ty plus nz times tz, just a single term, because the resulting matrix is 1 by 1. And that essentially is the dot product of any two vectors. So dot product is simply n transpose t. Now let's say I want to optimize, okay, minimize or maximize this quantity with respect to n, or nx, ny, nz. Okay, so I want to adjust these three variables. So this thing defined as this quantity, summation over I, or rather it should be this quantity, um, n dot sigma times n. Okay, so this is what I'm trying to uh, make the largest. Okay, but then you need to understand this n is a unit normal. Okay, otherwise if I want to maximize this quantity, I can simply take nx, ny and nz to be infinite values. Okay, but n is there is a constraint, so this constraint must be satisfied. So this thing subject to, okay, uh, mm, n dot n, or n transpose n, or I can also write this quantity to be um, n transpose sigma n. So basically n transpose sigma n is what we are trying to maximize, subject to n dot n equals 1. Okay, so what we would be doing is we would bring in something called Allegra multiplier, and we are not now optimizing Tn but Tn star, and that quantity is n transpose sigma times n plus lambda, which is a Allegra multiplier. So which is also an unknown. Okay, so this time I'm bringing in four unknowns, and I'll explain how that does that help. Okay, so 1 minus n transpose n. Okay, now when this condition is satisfied, this quantity itself is 0 multiplied to lambda. So what you are essentially optimizing, as long as you satisfy this, you are simply optimizing this. If you obey that, this equation is valid. Okay, and after that you can optimize nx, ny and nz, then you are simply optimizing this quantity. Okay, so if I really look into this, first of all, how do I optimize any quantity with respect to other? So when let's say if I want to maximize sine of x with respect to x, so I'll take ddx of sine of x and set it to 0. But that's when this is a total derivative, and sine of x is just a function of x. But in this case there are four unknowns that are there. Okay, so instead of taking a total derivative, I should be taking a gradient. Okay, gradient of with respect to this vector, which has the entire n vector and lambda. Okay, so it's a vector with four rows: nx, ny, nz, and then lambda. So with respect to that, I'm taking derivative of this quantity, and each quantity of each row, okay, should be equal to 0. So this equals a 0 vector with four rows. Okay, so that would be giving us first of all, the first three rows will give us this vector equation. Okay, and it can be shown for each component. Okay, you need to understand that each component is independent of the other. If you use that, this can be shown that the first three rows give us this equation, lambda times n, and which is the eigenvalue problem. And and the mm, and the one with the lambda simply gives us n transpose n equals 1. So you are now satisfying, this is a scalar equation. It's involving a dot product, so it's a scalar equation. And this is a vector equation. So you are simultaneously satisfying 4 equations. Okay, and by satisfying those 4 equations, you will be identifying 4 unknowns that are there. Okay, so it's a legitimate way of getting the solution. And by bringing in the Allegra multiplier, you're essentially making the constraint equation as one of the equations that needs to be satisfied simultaneously with every other equation. Otherwise, this nx, ny, nz could be infinitely large, positive or negative, to give you an optimum value for Tn. Okay. And there was no solution with this. So by incorporating this constraint equation, okay, you will be able to solve the system. Okay, so both set of equations should be satisfied simultaneously to give you uh, the principal values. Okay, so is it clear up to this point?
Yes.
You don't seem confident. Eh, if you want
স্যার
to
ওই
clear you,
ভেক্টর
yes, which part?
স্যার ওই ভেক্টর ইকুয়েশনটা কি করে এলো আমি বুঝতে পারিনি।
Vector equation ta ki kore elo? Okay, so you see, the vector with respect to which am I taking the gradient, that has 4 components: nx, ny, nz, and then lambda. Now the first 3 component constitute n. Okay, so when I take derivative, so um, mm, let's say uh, let's say the first term. So this one is as we explained, this is summation over j ni sigma ij nj, right? So this is the first term. I'm just explaining the first term. Now let's take a derivative with respect to nk. Okay, now this k can be anything from x, y, z, right? And same thing applies to I, j, and k. But this time in this expression, because there is no repetition of index, okay, I and j, there is no summation over k. So k is a free index. Okay, so k is either x or y or z, whereas j is taking values, all the values. While the summation is happening, j is taking x value, j equals x, j equals y, j equals z, every value. Same thing applies to I. Now, you see, summation is a linear operation, and any linear operation, let's say, is kind of transparent to derivatives. So the derivative simply enters into the summation, and I'm not writing the indices right now. Summations, double summations. Then first thing would be del ni, del nk, sigma ij, nj, and then another summation, double summation, ni sigma ij, del nj, del nk. Now, as I mentioned, that we are considering all the indices independent of one another. Okay, actually they are not, because they need to satisfy that nx squared plus ny squared plus nz squared equal to 1. But then modifying the optimization function and bringing in a Allegra multiplier, we can simply treat them to be independent, which basically means that, let's say, del nx del ny is 0, and del nx del nx equals 1, which basically makes it a Kronecker delta. So if it is a Kronecker delta, I can simply write it to be delta jk, and over here it to be delta ik. Now delta ik is uh, is uh, is so k is the free index, I is changing, so k is fixed, I is changing, I is taking the values of x, y, and z, whereas k is either x, y, or z. Okay, let's imagine k is x. So when I equals y, this thing is 0, this whole summation is wasted. When I equals z, uh, this whole summation is wasted because k equals x. But then when I is also x, then the value of delta xx would be 1, which would basically mean this when I equals k, this thing survives. Okay, so I can now write it to be an equation involving j, summation involving j, and I being substituted to k. That is the only term that survives. So there is a summation over I, but only the terms involved where I equals k will survive. So sigma kj nj. Okay. Similar, this term becomes summation over I, sigma ik in I, sigma ik sigma ik in I. So basically, this summation, I just didn't think that I should be using. Acha. So you need to understand this j is a dummy index. So instead of writing j, I can simply write I. So this thing becomes sigma kj, sigma ki in I, and sigma ik in I. Okay, I was a bit confused uh, because this thing only applies to symmetric tensors. Okay, so symmetry has to play a role. I forgot that needs to be taken into account. So that is only happens with the symmetry around. So sigma ik is sigma ki. So basically, I can put a 2 in front of it. Okay, and when you do the same operation with this, please understand n transpose n is like n transpose I times n, and I, the identity matrix, is another symmetric matrix, and in the similar way you'd get the similar expression. So this quantity is essentially sigma times n, the kth component. Okay, so similarly we would be having, see, lambda is not something that you can take derivative with respect to nx, ny, or nz. So they are independent. So that part goes to 0. The first term goes to 0. Then this whole thing, let's say del nk tn star, considering sigma to be a symmetric matrix, this turns out to be your mm, twice sigma times n kth component minus, and this time you see I times n is simply I times n kth component. Okay, and that is true for component by component. Okay, so and this equals to 0, right? So you can divide both sides with 2. That implies that sigma times n, acha, there would be lambda over here, is lambda times n. Is it clear now?
Yes, sir.
Yes, sir.
Okay, so it stop here. We are already past 1 hour. Okay, so we are already past 1 hour, so we would stop here. And we couldn't cover a lot. We are going slow, but as long as you are understanding, that is fine. I'm absolutely fine with that. And we'll proceed from here on the next class, so which is on Monday. So Monday, preferably at 9. If you can join the class at 9, that would be fine. If not, please let me know, so we'll have the class from 10. Okay.
Sir, not okay, not 9 p.m. 9 a.m. Okay.
Okay.